Hello everyone. Today I'll be talking about the BigO notation. So before introducing the BigO notation, I first talk about the concept of the function growth. To illustrate this, let me give you a example. So suppose there are two banks here, Bank A and Bank B, and now you've got like $100 and you want to store in either Bank A or Bank B. And then the policy of Bank A is that when you get the money back, you have like double the money. So you get like $200 back. And then the policy for Bank B is that they hold an interest rate of 5%. And in this case, you want to see like to choose which bank to store your money. And then suppose if you only store the money for 1 year, then definitely you'll choose Bank A. However, suppose you can like store the money for 100 years, then Bank B will definitely be a better choice. So let's write down the equations here. So for Bank A, so suppose the money that you currently have is like N, and then if you like store it for like for T years, so for Bank A, basically everything you get is always like 2N, and for Bank B, what you have is like N times, since the interest rate is 5% to the power of T. So now, so as we have seen here, so if it is only 1 year here, then everything you have is like, if it's 1 year, then everything you have back is 200, it's 2N. And then for Bank B, everything you have back is 1.05N. However, if there is like 100 years, it's still 2N here, but here you can have 1.05 to the power of 100 times N. And in terms of we plot the growth of the function here, this is the year, this is the money you can get back. So for Bank A, it will be always like 2N here. And then for Bank B, it's something like this. This is B. This is A. So what we want to do is that we want to know that when we have like so many years, we want to know what the property of the function growth will be, so that we can know better about. So if we can like store it for like even like 10,000 of years, which bank would I choose? So here we will introduce the concept of the BigO notation here. And I will first try to write the definition for BigO, like the definition. So normally we write that function f of x is BigO of g of x. And in this case, we would want to say that we can find a constant number n, and also another positive number x0, such that for all x, we can for all x that is greater than x0, we always have that fx is smaller than m times g of x. So this is the definition here. So let's first see like why we want to have a scalar m here. So basically, scalar m is saying that since we only care about the growth of the function, so and also since, for example, here, so if I say to store it for like tens of thousands of years, So even if I increase, so if I increase my origin amount of money from 100, say if I multiply 3 times to 300, the influence is much smaller than if I change the interest rate from 5% to 6%. And in that case, we can normally ignore the constant term in the front. So basically, we can say like if we can find any m that is constant, it should work. So m can be like either like 1,000, like 10,000. It doesn't matter here. Because this will be satisfied for all x greater than x0, which means like it will satisfy for like as many years as we can have in this function here. And then let me give you some examples about about the some common functions and their corresponding like big O bounds. Yeah, so actually since we can see it's like smaller than smaller or equal to sign here, so the big O notation will normally impose an upper bound. So basically, if we say like some function is if we say like some function is O of n squared, so it can either be like it can either be like n squared or like 3n squared, and or like 1 over 3n squared. It can even be like n or 0. Since it's an upper bound, so these can also work. And then let's analyze the big O for some common functions here. So first is about the polynomial functions. Maybe we can write a simple polynomial as like x cubed plus 2n squared plus 3n plus 1. So suppose this is our polynomial function. And then to deal with this case here, sorry, f of x. To deal with this case here, like we can see that the growth term of the term with the highest coefficient is the fastest. With the highest exponent is the fastest. So no matter what the coefficient is. So even though this coefficient is 3, this still grows faster here because if we plot it, 3x is something like this, but if it's x cubed, then it will be something like this. So as x goes to very large, this will be much larger than this term here. So normally for this case, we only pick the term with the highest exponent order. So which we write as equals to g of x cubed. And we can also check like if there are some exponential terms. So suppose if I have exponential terms plus x to the power of 3. So the thing is that the exponential term will increase faster than all the polynomial terms. So we write it as equals to g of exponential of x. So yeah, normally if we like rank all the common terms in terms of the growth rate, it's something like this. If I so if I have like x cubed exponential of x and log of x or x this, so maybe here's a question for you to think about. Like if you want to order all these terms here, like which of the function here will have the highest growth? Does anyone have some ideas? Okay, so a very good way is, so you can either try to like plot these functions and see how they appear at the infinity here, and uh, another way is that we can write some mathematical notations here, like limit x goes to infinity. Suppose we don't know like for this term and this term here, we can write like limit x goes to infinity. So what uh, will this go to zero or will this go to infinity here? And then we can check that as x is going over e, so the so every time x increase by one, the top term will be multiplied by x, while the bottom term will be only multiplied by e. So in this case, this will goes to infinity, and so we write like, hmm, so we will rank them in the order of this. Hmm, so I'm ranking it in terms of the growth rate. And in this case, we can see like, um, so basically we can pick any function of the left, and we can say it's using big O notation of a function on the right. So for example, log of x equals to O of x. Yeah. So that's all for the big O notation. Thank you very much.